Hey guys, sorry I couldn't be with you today, but I wanted to go over the guided notes with you. So today we are going to talk about vertex form and stretch, compression, and reflection. So remember yesterday we looked at the vertex form of the quadratic equation. So that was in the form of y equals a times x minus h squared plus k. And yesterday we talked about what the h and the k do. They determine our new vertex. Remember, you take the opposite of the h value and you keep the k value. But we didn't talk about the a value yet. That's what we're going to talk about today. So today we're going to alter the parent function in other ways using a. And sometimes you'll hear that called the leading coefficient. It's leading because it's out in front. So here is a chart to help you do some discovery. Remember yesterday you did some discovery in your calculator. You're going to do the same thing. You'll graph x squared. This is the parent function. So are there any changes from the parent graph? No. So this is your baseline, your control. And then all these new ones we're going to graph are going to be based on the original. So pause the video real quick. Take some time to put all these functions in your calculator, make a quick sketch and write down the changes, and then start the video again to check your work. All right, so you've completed these 5 things, so let's go through them. First of all, if there is a minus sign in front, the change from the original graph is that it now opens down. And a sketch of that would look like this. Okay. For this one, y equals 2x squared, the change from the original graph is that it is vertically stretched. So when we stretch a graph, we stretch it vertically, in other words, up and down. So think about a rubber band that you're pulling up and down. It gets taller and skinnier, and so does our graph. So here, we have a 1/2 out in front, so that does something a little bit different. 1/2 makes things shorter and skinnier, so we call this a vertical, or we're going to say it was vertically compressed. And a compression means that you are making things shorter and fatter, so we're going to squish things down vertically. So I call these Danny DeVito parabolas. Okay, so this is a combination. We've got a negative, and that makes it open down. And we've got a 2, which makes it a vertical stretch. Now, you don't have to say vertical every time. That's assumed. I just wanted to make sure we said it now so you wouldn't think horizontal. So I'm just going to write V period to stand for vertical, and it is a vertical stretch. So it opens down, and it's skinnier than the parent graph. Same thing with the next one. It's opening down, but this time we've got a 1/2, which will make it shorter and fatter than the parent graph. So it will open down, and that is a vertical compression. So it will be upside down and shorter and fatter. So this is what the a value does. Sometimes it's positive, sometimes it's negative, sometimes it's between 0 and 1, and sometimes it's greater than 1. So a is greater than 0, does the graph open up or down? That means if a is positive. So if it's positive, then the graph opens up. If a is less than 0, the graph opens down. So the sketch would look like this versus this. If a, and those bars mean absolute value, so whether it's positive or negative doesn't matter if that a value is bigger than 1. So whether it's positive 4 or negative 4, does it stretch or compress? It stretches. And if a is between 0 and 1, so something like 1/2 or 2/3, that is a compression. It gets shorter and fatter. So something skinnier versus something shorter and fatter. So the next thing we're going to do is fill in this chart to practice identifying what different a values do. But we're also going to remember yesterday when we found the vertices of each function based on the equation. So let's first look at this function and say, does it open up or down? Well, earlier we found that if a is positive, it opens up, and if a is negative, it opens down. So let's go through this whole column. This is positive out in front, so it opens up. This is negative out in front, so it opens down. This is positive in front, so it opens up, and this is negative in front, so it opens down. Now we're going to look for a stretch, a compression, or neither. So it will stretch, whether it's positive or negative, if the value is bigger than 1, and it will compress if the value is between 0 and 1. And if it's just 1, in other words, if there's nothing there, we'll pick neither. So here we have a 3. That 3 stretches our graph. Here we have an imaginary 1, which means nothing changes, so we're going to say neither. Here we have 1/4, and that's between 0 and 1, so that's a compression. And here we have 2. Even though it's negative, it's still greater than 1, and so it is a stretch. It's going to get taller and skinnier. It's just going to open down instead of opening up. Now let's do the vertex, and we're going to get the vertex from what we did yesterday. Remember, h and k are included now. So remember, our h lives inside the parentheses. Here, remember from yesterday, y equals a times x minus h squared plus k. H is what's inside the parentheses and k is what's outside. So here, there's not even parentheses, so we can assume that there's a 0 in there. And then k is on the outside, so that's -2. Here, the h is -2, but remember yesterday we did the opposite, so that's going to be +2, and then the k is 5. Here, the h is going to be 1, so we're going to do -1, and there's no k, so we're going to say 0. And then here the h is +3, so we're going to say -3, and the k value is -4. So these are all the vertices. We found these yesterday and we graphed based on those key points, but now we're going to start stretching and compressing and having them open up and down. So how can you tell if a vertex is a maximum or a minimum without graphing? We can look and see if it opens up or down. So if a parabola opens up, then we know it's going to have a minimum, and if a parabola opens down, we know it's going to have a maximum. So that's all you need to do today to get your homework done. So please work hard on your homework, and I will check it when I get back, and I hope you have a good weekend. Bye.